what if I told you that the entire modern framework of global science, like everything from the engineering needed to fuel rockets to the super precise synthesis of life-saving medicine, was basically reverse engineered from a single glass of water?
I mean, it sounds like a massive exaggeration.
Yeah.
Or, maybe the setup to a really strange riddle.
Right.
But the wild thing is the way humanity actually measures the physical universe, like
Yeah.
how we fundamentally agree on the concept of reality, really does trace back to something that totally mundane.
Which is just crazy to think about. Welcome to the deep dive. Okay, let's unpack this because our mission today is to look at the invisible scaffolding that kind of holds the physical world together.
Yeah, the stuff we completely take for granted.
Exactly. We are diving into a concept that you probably interact with every single day without even realizing it, the kilogram per cubic meter.
It sounds super technical right out of the gate, I know.
It really does. But whether you're studying for a physics exam or um, trying to troubleshoot why your international baking recipes always come out super dense and flat, or you're just intensely curious about how humanity imposed order on a chaotic universe, this exploration will completely change how you look at the space around you.
Absolutely. And we're pulling this directly from the official documentation on the kilogram per cubic meter.
Actual literal Wikipedia standards.
Right, the official definitions.
Yeah.
And what stands out immediately is the formal classification. It's designated as the standard SI-derived unit of density.
SI being the International System of Units, right?
Exactly, the metric system's formal name.
Okay, let's pause on that phrase for a second, specifically the word derived. Because the source material doesn't just call it a unit, right? It calls it a derived unit. So what separates a derived measurement from just a regular one?
Well, think of it through the lens of fundamental reality. Like, there are certain properties of the universe that just exist independently.
Okay, like what?
Like distance. Distance is one. You can literally take a ruler and just measure the length of a piece of wood.
Right, it's just there.
Yeah, and mass is another one. You can take a stone, put it on a balance, and determine its mass. In the metric system, the meter and the kilogram are what we call base units. They're the foundational building blocks.
Got it.
But density is not something you can just, you know, hold a single physical tool up to and measure directly in that exact same way. It's a relationship.
So density doesn't really exist on its own. It's kind of born out of this like mathematical marriage between mass and volume.
Yes, that is a perfect way to put it. You derive it, you take that fundamental concept of mass, the kilogram, and you literally divide it by the fundamental concept of volume, which is the cubic meter.
Oh, I see.
It basically translates a physical state into a universally understood ratio. It just tells you how much stuff is packed into how much space.
Okay, so picture this. I want you to visualize a massive, completely empty box, like a perfect cube.
A very big box.
Yeah, exactly. 1 meter tall, 1 meter wide, and 1 meter deep. It's large enough that you could like comfortably curl up inside of it.
That's a great mental image.
Right. Now, if we just start throwing materials into this giant box, say we fill it entirely with loose feathers,
Okay.
and then we take another identical box and fill that one entirely with solid iron.
Uh-huh.
Both of these boxes are taking up the exact same amount of physical space in the room. But the mass inside them is, it's wildly different.
Right. And that visualization right there is the crucial first step to really understanding the brilliance of the SI system.
Because before this, how do people even talk about it?
Well, before this kind of standardization, human language basically relied on highly subjective terms. People would just say something was heavy or light.
Which means nothing, really. Heavy compared to what?
Exactly. A pound of feathers and a pound of iron have the exact same mass, but they occupy totally different volumes. So by creating the kilogram per cubic meter, scientists essentially stripped away all that human subjectivity.
I do have to challenge the physical reality of this, though.
Okay, go for it.
Because if density is just a derived mathematical equation, like literally just kilograms divided by cubic meters, is it really just a convenient formula we invented to describe how tightly packed a box is? Or is it a genuine intrinsic property of the material itself?
Oh, no, it is absolutely an intrinsic property. And that is kind of the major philosophical leap that the derived unit makes.
How so?
Well, the equation is just our human translation, right? But the density itself is the actual physical truth of how closely the atoms and molecules of that specific material are bound together.
Oh, wow. Okay.
Yeah, the kilogram per cubic meter just gives us this standardized lens to view that microscopic reality on a massive macroscopic scale.
So it scales up perfectly.
Exactly. If
Yeah.
I tell you the density of a material in kilograms per cubic meter, you instantly know how it behaves physically, regardless of whether you have a tiny pebble of it or like a massive mountain of it.
It creates a baseline. It gives humanity this shared objective language.
Right.
And here is where it gets really interesting, because once you establish this massive, invisible 1-meter box as your baseline, you have to figure out what to put inside it to actually anchor the system, right?
Right, you need a standard.
And the source material hands us this incredible fact about water. The density of water is about 1,000 kilograms per cubic meter.
Which is a very neat number.
Exactly. If you fill that giant box to the brim with water, it holds exactly 1,000 kilograms. And mathematically, that scales down perfectly to 1 gram per cubic centimeter.
The symmetry of those numbers is just striking. It transitions so smoothly from the macroscopic, the giant box, straight down to the microscopic, the little cubic centimeter.
But, I mean, the perfection of those numbers gives me pause.
Why is that?
Because 1,000 kilograms, exactly 1 gram. The universe is incredibly chaotic and messy, you know? Are we really supposed to believe it is just a massive lucky coincidence that the most abundant liquid on our planet happens to fit so flawlessly into our math?
Well, what's fascinating here is that it's not a coincidence at all. The entire system was actively engineered to produce that exact result.
Wait, really? They rigged it?
They totally rigged it.
Yeah.
When the foundations of the metric system were being laid out way back during the French Revolution, the creators weren't just discovering these numbers out in the wild, they were dictating them.
Oh, man.
Yeah, the source notes this profound historical anchor. The size of the gram itself was originally defined as the mass of 1 cubic centimeter of water.
So they didn't, like, build a system and then measure water to see where it fit?
Yep.
They looked at water first and built the entire system of mass around it.
They completely reverse-engineered the math from the natural world. Think about it. If you want to create a measurement system that the entire globe can actually adopt, you can't base it on some rare mineral.
Right, or a specific piece of metal locked in a vault in Paris.
Exactly. You need to base it on a substance that literally every human being on the planet has access to. Water is the universal constant of the human experience.
That is so smart.
Right. By defining mass through a specific volume of water, they basically ensure that anyone, anywhere, could theoretically reproduce the standard.
You know, that drastically changes how you view the metric system.
How do you mean?
Well, it often gets criticized, especially by people who grew up used to pounds and ounces, as being this really cold, sterile, highly academic set of numbers.
Oh, sure. Just abstract math.
Yeah, but it's actually the complete opposite. It is profoundly grounded in the physical reality of nature. Like the mass, the volume, the water, they are all talking to each other in this incredibly elegant language of ones, tens, and thousands.
It is pure intentional design. And once you grasp that the mass of a cubic centimeter of water is exactly 1 gram, the whole metric system suddenly just feels intuitive.
It really does.
It stops being this thing you have to memorize and becomes this logical web of interlocking relationships.
But, okay, that brings up a major point of friction in our source material.
Okay, lay it on me.
We have this beautiful water-based master unit, right? The kilogram per cubic meter. It is the official grand champion of the International System of Units.
Gold standard.
Right. But then the text reveals this weird bit of a scientific rebellion. It explicitly notes that in the field of chemistry, grams per cubic centimeter, so GCM/SIVO, is the much more commonly used metric.
Ah, yes, the chemists.
I have to admit genuine confusion here. If kilograms per cubic meter is the universally agreed upon standard, why are chemists completely ignoring it? Doesn't having two different metric standards operating at the same time kind of defeat the golden rule of having a universal system?
I mean, it definitely seems contradictory on the surface, yeah. A universal system implies universal adoption.
Right.
But this deviation really just comes down to the friction between theoretical physics and applied daily physical reality. Chemists are basically adapting a very rigid system to fit the human scale of their work.
So is it kind of like, I don't know, a carpenter trying to measure the length of a small wooden chair in miles?
Yes, exactly that.
Like, sure, mathematically you could figure out exactly what tiny fraction of a mile that chair is, but it's an entirely useless scale for the actual job.
That analogy hits the core of the issue perfectly. It is all about cognitive load. Consider the actual environment of a chemistry lab, you know? What are the physical objects these scientists are manipulating every day?
Little stuff. Test tubes, small beakers, pipettes.
Right. They are measuring liquids in tiny fractions of a liter. They are not managing giant 1-meter vats of industrial chemicals.
The physical space they operate in is basically tiny.
Exactly. So a cubic centimeter is a volume they can actually hold in their hand. They can visualize it instantly. But, the advantage goes way deeper than just physical visualization. It fundamentally changes the mental math.
How so?
Let's look at water again. In the chemist's preferred unit of grams per cubic centimeter, the density of water is 1. It is a perfect, beautiful whole number.
Rather than 1,000.
Yes. And in chemistry, you are constantly comparing the density of new compounds, solutions, and mixtures against the baseline of water. This is what we call specific gravity.
Okay, tracking with you.
So, if a chemist synthesizes a completely new liquid and they force themselves to strictly use the official SI unit, they have to run all their mental comparisons against the number 1,000.
Oh, I see.
They have to ask themselves, okay, if water is 1,000 kilograms per cubic meter and my sample is 1,250, what is the ratio? It requires deliberate calculation every time.
But if they use the smaller scale, the math essentially just does itself.
Bingo. If water E1 and the new liquid is 1.25 grams per cubic centimeter, the comparison is instant. It is exactly 1.25 times denser than water.
That is so much easier.
Right. By shrinking the box from a massive cubic meter down to a tiny cubic centimeter, chemists kept all the elegant logic of the SI system, but they just optimized the proportions. They drastically reduced the cognitive load required to do their actual daily bench work.
So they didn't break the rules at all. They just exploited the perfect scalability of the metric system.
It's a completely pragmatic adaptation. The fundamental relationship between mass and volume stays completely intact. They literally just shifted the decimal point to a place where human error is way less likely to occur.
Okay, and that focus on human error provides a really perfect transition here.
Uh-oh. I know where this is going.
Because up until this point, we've enjoyed a very neat, pristine world, right? We have the exact math of the metric system, this beautiful historical connection to water, the very logical adaptations that chemists make. It all feels so clean and mathematically sound.
That sounds just very satisfying.
But then we hit the conversion section of the source material. And this is where that flawless system crashes headfirst into the very messy, chaotic, historical reality of American and British industry.
Yeah, the collision of completely incompatible frameworks. It's a very significant shift in the text.
It is pure chaos.
Yeah.
I mean, just looking at the raw data gives you a sense of cognitive whiplash.
It really does.
The text makes this very stark, unavoidable distinction between exact conversions and approximate conversions.
Which is a huge red flag in science.
Huge, because within the metric family, everything remains exact. 1 kilogram per cubic meter is mathematically identical to 1 gram per liter, which equals exactly 0.0001 grams per cubic centimeter. The certainty there is absolute.
Yeah, it's locked in.
But the second we leave the metric system and enter the realm of imperial and U.S. customary units, the word exactly completely vanishes. It is entirely replaced by approximately.
And if we connect this to the bigger picture, that single word change is arguably the most dangerous concept in global engineering.
Wait, really the most dangerous?
Think about it. Exact implies a mathematical absolute. You can scale an exact number to infinity, and it will always remain true. But approximate, that implies an inherent margin of error. It means someone somewhere is rounding off.
And the numbers they force you to round off are just staggering. Like 1 kilogram per cubic meter is approximately 0.06243 pounds per cubic foot.
Yikes.
But wait, it gets worse. The info box in the article takes it even further, listing the conversion as 0.0624279 pounds per cubic foot.
That is just painful to listen to.
That string of decimals is a total nightmare. If you've ever tried to follow an international baking recipe, this is that exact nightmare. It's like translating a super dense legal contract through 3 different languages using a cheap dictionary.
That's a great way to put it.
Eventually, that approximation is going to cause a crucial clause to mean the exact opposite of what you intended.
Your analogy of the legal contract is incredibly apt. Because in engineering and international trade, these conversions function as legally binding parameters.
Oh, wait. Millions of dollars are on the line.
Exactly. When you rely on an approximate conversion, you have to make a human decision. Do you round to 2 decimal places? Do you use the full 8 decimal places provided in the info box?
Then someone has to choose.
Yes. And every single time you round that number, you are either mathematically creating mass out of thin air, or you are mathematically deleting mass that actually physically exists.
On the scale of baking a cake, that rounding error might just mean your dough is a little too dry. But what happens when we scale that up?
Well, you get compounding catastrophic failure.
Yeah.
Think about fueling a spacecraft
Right.
or, a massive cargo ship transporting liquid natural gas across the ocean. When you take an 8-decimal approximation and multiply it by millions of gallons, that tiny little fraction of a rounding error compounds into thousands of pounds of unaccounted for physical mass.
So the ship just weighs more than you thought it did.
A ship sits way lower in the water than it was engineered for. Or a rocket literally runs out of thrust seconds before reaching orbit because the physical mass of the fuel in the tanks didn't match the mathematical approximation in the computer.
The math says you have enough, but the physical reality completely disagrees.
It's terrifying, honestly.
And the source highlights another layer of this chaos that feels like a literal trap waiting to be sprung. It compares the conversions for gallons.
Oh, the gallons, yes.
1 kilogram per cubic meter is approximately 0.1335 ounces per U.S. gallon.
Okay.
But it is approximately 0.1604 ounces per imperial gallon.
Right.
And they both use the exact same word, gallon.
Two entirely different physical volumes, just hiding behind identical terminology.
It's madness. If you are an engineer collaborating internationally, not only do you have to manage the compounding danger of the decimal approximation, but you also have to, interrogate your colleagues about which specific historical version of the word gallon they happen to be using today.
Are we using the London gallon or the New York gallon today, boss?
Exactly. It's absurd.
But this specific discrepancy perfectly illustrates why having an internationally agreed upon, completely exact baseline isn't just some academic luxury. It is an absolute necessity for modern civilization.
You literally can't build things without it.
Without the kilogram per cubic meter acting as this universal translator, global scientific collaboration and industrial trade would just become hopelessly bogged down in a mire of compounding conversion errors. You absolutely need one metric that possesses zero geographical bias.
A language without an accent, so to speak.
Precisely. A standard that means exactly the same thing down to the molecular level everywhere on Earth.
Which brings us to the ultimate question of this deep dive. So, what does this all mean?
It's a journey, for sure.
We've journeyed through the anatomy of a derived unit. We visualized that massive 1-meter box. We uncovered the really beautiful historical poetry of reverse engineering the diagram from just a simple cubic centimeter of water.
We covered a lot of ground.
We did. We explored why chemists shrink that box down to save their mental bandwidth. And we waded through the, frankly, terrifying compounding dangers of approximate conversions in global engineering. But as we look at the external links section of the source material, it points us toward a totally fascinating final thought.
Yeah, it directs the reader outward to the official BIPM definitions of the kilogram and the meter.
BIPM being the, what is it?
The intergovernmental organization through which member states act together on matters related to measurement science. They are essentially the ultimate keepers of the standard.
Right. They're the ones who officially define reality for the rest of us.
Pretty much.
But here is the hook. We spent all this time today marveling at how perfectly water anchors the metric system, right?
The beautiful 1-to-1 ratio.
Exactly. 1 gram is exactly 1 cubic centimeter of water. But the text used a very specific phrasing. It said the gram was originally based on water.
Originally. Past tense.
Past tense. If water is this universal, elegant constant, why did the BIPM have to redefine it?
Well, because as our technological capabilities expanded over the decades, our tolerance for approximation basically shrank to near zero. And we discovered that our beautiful universal constant was actually fundamentally unstable.
Wait, unstable how? I mean, it's just water.
The density of water is not a static monolith. It is highly reactive to its environment. If you take that cubic centimeter of water and just heat it up a little bit, the thermal energy causes the molecules to become excited.
Okay, that makes sense.
They move faster and they spread slightly further apart, which means the water physically expands.
Wait, so if the volume expands, but the amount of actual water molecules remains the exact same?
The density decreases.
Oh, wow.
Yeah. A cubic centimeter of warm water actually has less mass than a cubic centimeter of near-freezing water. Furthermore, the atmospheric pressure pushing down on the water also alters its density.
That is wild.
So that perfect 1,000 kilograms per cubic meter, it really only exists under highly specific, laboratory-controlled temperatures and pressures.
That kind of shatters the whole illusion. I mean, the foundation of your entire global measurement system changes its physical mass just because the room got a little warmer. It's not a universal constant at all. It's just another approximation.
Exactly. And modern quantum physics, Nanotechnology, deep space navigation, they cannot function on approximations. They require exactness on an atomic scale. The variation in water, even though it's microscopic to human senses, became a massive structural flaw in the invisible scaffolding of science.
So the keepers of the standard basically had to abandon the very substance that gave the metric system its birth in the first place.
They had to divorce the definitions of mass and length from tangible physical objects entirely.
No more water?
No more water. They couldn't even rely on the physical metal cylinders they kept locked in a vault in Paris, because even metal degrades over a century. To achieve ultimate precision, they had to untether the kilogram from Earth entirely and tie it to the immutable, fundamental constants of the universe itself.
That is just a staggering philosophical shift.
It really is.
We started this journey with a very comforting, tangible image, a box filled with water, something you can feel, something you can drink. But as humanity's demand for clarity grew, we realized that the physical world is just too messy, too reactive to serve as its own baseline. We had to leave the water behind to find a mathematical truth that doesn't change when the temperature rises.
It's poetic in a way.
It really is. Thank you for taking this deep dive with us. The next time you encounter a seemingly dry technical measurement, or you find yourself carefully leveling off a cup of flour in the kitchen, take a moment to consider the invisible framework making that measurement possible.
Think about the giant box.
Yes. Question the approximations. Visualize those giant 1-meter boxes floating around you and keep looking for the hidden chaotic history behind the everyday numbers that order our universe.